Hi everyone, my name is Robert. I'm here to talk about absolutely nothing to do with Ruby today. I'm going to introduce a language called Clojure, which is a functional programming language, and a database built on top of Clojure, an immutable database. And I'm just here to show you what it's about and hopefully expand your world a little bit. So first, Clojure. Clojure is a Lisp, which you've seen a little bit about earlier today. It's a purely functional language. It's an immutable language, and I'll talk about that in a sec. It's dynamic. It runs on the Java and the JavaScript VMs, and I think you guys will like the JavaScript side of it more than the Java side. It's open source, and it's quite old now, 7 years old. Lisp. So that's Lisp at the top. That's a Clojure function definition, and the obligatory XKDC comic. And that really captures it, I think. So Lisp is actually really old. It's over 60 years old now. And the reason why it didn't catch on is because the hardware we had back then wasn't strong enough to support it. And now we have such great hardware, such cheap hardware, it seems to be making a comeback. And I'm hoping to help that along. So functional programming, essentially, is programming with functions. We can do it in Ruby, JavaScript. We can't really do it in Java because we can't pass functions around. But any language that you can create, pass functions by reference, use them in other function calls and higher order functions, that's functional programming. And good functional programming tries to use pure functions as often as possible. That is, functions that operate purely on their inputs rather than reading something, mutating some state off to the side like a database, and then returning your data. You want functions that are what we call idempotent, pure. They're very easy to reason about, to think about, and to compose, and they're very easy to test. In fact, if you write mostly pure code, your test base is actually a lot smaller because the code is actually simple enough that you don't need tests for them. That's functional. Defining and calling functions, we saw this a little bit earlier. So this is a pretty simple function, and something to notice about this is that this is really just a nested list of lists. We define a function, we have a doc string for it. It takes a single function and argument called num, and then we use if to check if it's a number, and if it is, we multiply, and if not, we just return it. And then below you can see we've got some invocations there, and that's Lisp. You all know how to read and write Lisp now. So persistent data structures, immutable persistent data structures. This is really the key value to using Clojure, I think. Once you define a composite data structure in Clojure, it cannot change. You can make copies that have changes applied to them, but the one that you define in the beginning, if you have a reference to it, it cannot change, no matter what. That's quite a stark contrast to Ruby, where you can literally change everything. Monkey patching is the word we like to use. And in Clojure, once you've defined something, that's it. If you have a reference to it, it will never change. So designing code and websites and applications around that, it's a lot easier to think about the life cycle of your application when you don't have to defend against state mutating over time. Getters and setters, don't need those. Many of your unit tests just melt away because most of your unit tests are testing what happens when you change state, when you mutate state in place. So by using immutable data, we write far less code, and the code that remains is a lot easier to read and understand. So if you had to do this in another language that doesn't have what this persistent bit is, you would have to create deep copies of each object every time you wanted a new change of an object, if you wanted to keep the original object intact. In Clojure, because data is immutable, it can actually share structure internally. So you might have a map with, or a vector with 3 items. You create a new copy of that vector with a 4th item. That new vector is actually just pointed to the original vector plus that 4th item. And the entirety of all the immutable data structures in Clojure work that way. So it's actually far more performant to work with than working with defensive decopying like they do in Java. And yeah, again, far easier to reason about. To me, after using Clojure for a couple of years, this is what working with mutable state feels like. Horrible. Okay, so Clojure's collections. There's only really 4 base collections. There's lists, which are good for sequential access, working through a long list, one by one. Vectors, which are like lists, except that they support, they're performant for random access, so you can look in the middle, you can take subsets from the middle, and that kind of thing. You have maps, which are your traditional key value stores, and it's important to note that anything can be a key or a value. You're not restricted to only strings or only integers for keys. And then sets, which are basically enforce that you only have one of any particular item in the set. You have things like set differencing and intersections and those kinds of things. And you can compose all of these arbitrarily, and we do every day. And these are all using that immutable capability that Clojure has. So they all do the structural sharing internally. Okay, so that was the, I think, 5-minute introduction to what Clojure is. So essentially, the way that when we write Clojure and build Clojure programs, we're trying to do the first bit. We're trying to just create sort of anonymous vanilla data structures using those core collections and passing them through pure functions one by one until we have the result that we're looking for, rather than creating a big object-oriented type hierarchy, stuffing data into it, and then calling methods on that to try and get the result that we want. It's very easy to reason with object-oriented things like that in the small, but as anybody who's built a big system knows, trying to do that in the large, your test bases grow dramatically big, and it just becomes really hard to reason about. Whereas a pure function will always be pure, it'll always be simple to use. And again, as I've said many times, easier to compose and test. So that's Clojure. On to Datomic. So you can all read that. So Datomic is different to things like MongoDB, and well, I actually don't know much about other NoSQL databases. I haven't used any, but I know that there's this term bandied about, eventually consistent. And what's important to know about Datomic is that it isn't eventually consistent; it's consistent. It makes quite a big difference when designing and building applications. So we'll dig into some of the. Okay, before we get into the details, it's important to know that it is closed source and it is proprietary, and you do have to pay for it if you want something running in the large. But there are free editions. You can grab Datomic free, which you can use forever. It's free, it's got an open distribution. You can use it in open source, no problem, but you're limited by the number of active processes you can use. And then there is a starter edition of Datomic, which is sort of one up from that, which allows you to use the different backend storages that it supports. And then you get the paid one, which is the full Monty. They are looking at ways, I've spoken to the guys who built Datomic, Rich Hickey and Stu Halloway, and they are looking at ways to eventually open source Datomic. Once they become a huge funded company like MongoDB is, then they can do that. So I'm standing here today to slowly help that effort forward, to grow the people who use it, so that eventually, one day, it can be open source. So I'm going to talk quickly through Datomic's architecture, the way that you deploy its system, and then we're going to talk about the data model that's in that architecture. And once we've done that, we'll start looking at the code. And if you feel like you don't quite get why all this is important, it'll all start to come together when we're looking at the code. So please bear with me. So in the architecture, instead of having everything in a single process, like with MySQL, you've got storage, transactions, reads, indexing, it's all in one process. And when you use MySQL, you talk to, you send messages into it and it sends messages back out. What Datomic has done is broken that up into 3 pieces. The first piece is the transactor. And all the transactor is responsible for is writes. You tell it, put this in the database, and it will, in a serial queue, a single serial queue, it will make sure that they go in one by one. In any given system, you can only have a single active transactor. So for scale, people who've worked with large systems, you might ask, well, how does that scale? A transactor only has to do writes. It doesn't have to satisfy reads. It's an immutable data store. There's no locking. You don't need to lock your data at any point. There's no read locks or write locks. It's just appending data to the end of the immutable data store. So it can do that incredibly quickly. It also is responsible for indexing in the background, and it'll only do reads. It'll only use the read side of the Datomic API inside a transaction if you require it. So the typical thing of taking $100 here and putting $100 there, you need to read both accounts to make sure that everything's right inside the transaction process. That's the only time you do reads, inside the transactor. The second piece is storage, and storage can be anywhere. They've sort of abstracted storage away from the engine, and you can store it in memory, on disk, in any of these external storages. And Datomic was originally designed as a DynamoDB only product, but as they were testing it out, people, they realized that it was actually more universally useful than that. What's nice about this is if you do want to try Datomic out in your infrastructure, you don't have to, you can reuse your existing clustered SQL setup, or your existing React cluster, or whatever you may have, and not have to worry about data redundancy and everything, aside from what you already have. And the coolest part is the peer process, which is actually living inside your own app. So if you have a JVM-based website with 4 web servers, each of those web servers will have its own peer process or peer library built into the process. And when you read from storage, that peer is reading directly from storage. Read out the SQL cluster, the files on disk, what have you. It doesn't involve the transactor at all. And as it satisfies those reads, because the data is immutable and can never change, it can transparently cache those pieces of index segments in memory as it satisfies those queries. And those, because the data is immutable, you never have to invalidate those caches. So at Cognition, we're using this in production. We don't have a single line of manual caching code in our entire code base. We just do everything, we just use everything that Datomic provides with its caching. And it's all immutable, so we never have to expire cache. It makes for a lot less stress. So those are the 3 pieces that you get in the core Datomic architecture. There's a 4th piece that you can add if you have a paid license, and that's the second-tier cache. Using memcached. And basically, if you have those 4 web servers and you need to do a rolling deploy and take those processes down and bring them back up again, you're going to throw away all the cache that was in that process's memory. So to keep those peers warm, you have a second-tier cache for them to repopulate themselves off. So in our system, we are using memcached, and almost our entire website is served out of memcached, just because of the way that our Datomic is architected. We only really serve out of storage when people are accessing the brand new data that's been stored. But for the most part, it's served out of cache, again, without a single line of manual caching code on our part. And the other thing about paid licenses is that you can have a high availability failover pair for your transactor, which is quite important if you want to ensure you stay up all the time. Okay, so that was the architecture and how it's been broken up. Now we'll look at how data is stored in Datomic. So in SQL databases, you have sort of rectangles, tables, columns, and rows. In MongoDB, you've got documents, which are essentially collections of blobs, collections of things. Datomic doesn't do either, and instead, it'll just store these tuples or tuples, whatever you call them, of entity attribute value. And any entity can appear multiple times, any attribute can appear multiple times, and any value, of course, can appear multiple times. And you create knowledge by specifying multiple of these tuples or datums for a given entity. So for example, I like coffee. So my entity number is 123 in the database. Name is the attribute, Robert, and so on. So that's how we store sort of the now data, the data we have today. But what about time? There's a 4th value in that tuple that is sort of optional if you want to query against it or not, and that's the transaction that caused that tuple to appear in the data store. So looking at my entity, both of those EAVs or datums were created by the same transaction. So if I wanted to find out what time anything happened, I could just look at the transaction and use the transaction to find the timestamp. So you can write a million datums in a single transaction, or a single datum in a single transaction. And it doesn't matter, it will all link back to the same transaction. And transactions are themselves entities, which makes for really great. they're also entities. So if we now, so Datomic is an immutable database. How do you make changes? Well, you just transact new facts. So now I've transacted that I no longer like coffee and instead that I like beer. Important. You'll see that, the coffee is still linked to that old transaction and it's still there, but the beer value is now linked to a new transaction. So if I had to query against this database at the 789 transaction, I'm going to see that Robert likes beer. If I had to go back in time, which I'll show you just now, to the previous transaction and query what does Robert like, I'll see coffee. And this is a very small example, but it works universally across all of the data in your database. So you can imagine if you have a running system and you've got a weird hairy bug which you can't figure out what the problem is, with a system like this, you can literally go back in time and look at the whole world as it was on Tuesday last week and query against your logs, your transaction logs, which users were active, what products were in the database, what the prices were. It's all as it was last week. And then you can step forward and find the offending transaction and so on. So that's time. So how do we actually define what you can put into Datomic? When you specify a schema for Datomic, the only thing that you actually define is how those attributes work. So how name or how likes work in these examples. For each schema attribute, you define a minimum of 3 things: what the attribute is called, what its data type is, and whether a given entity can have one or more than one of them. And optionally, you can index them. You can assign a couple of uniqueness constraints types, and there's a couple other things which make working with entities or attributes en masse easy. Datomic does not enforce or prescribe how you combine attributes to create entities. So you could have a user in your database with just an email address, and then another user with email, full name, profile picture, an audit trail of everything he's ever done. And Datomic doesn't enforce you to have these empty fields, which is really, really nice. That's the data model. We can switch to the code. Okay, can everybody read that? Can anybody not read that? Okay, so this is Emacs. Sorry, Vim people. Okay, let me expand this up. How am I doing for time? Okay. So here I'm going to connect, just start a new Clojure namespace and pull in the Datomic API. I'm going to define the database URI, delete it, create it because I'd already done this, then connect to the database. So here, these are all just function calls, and this def here is just defining a name in this particular namespace with the value of the result of deconnect. So now I can at any time, I can go and look at the value of the connection, and I can see all sorts of interesting things there. So now I'm going to define some schema. So, okay, so I'm defining three attributes. Username, which is of type string, and entities can only have one at a time. It should be indexed so that I can get fast lookup. And then this stuff over here really just tells Datomic to install it as schema, so that when I query or when I try to look up things or try to transact things, that it knows that these are allowed attributes. The group name, same kind of thing, and the group users using the ref value type. So ref basically says the value side can be any other or any entity in the system, be it the same entity, a different entity. You can refer to schema or to transactions, doesn't matter. And we're saying that groups can have many users. So we'll just define that. Okay, and now we'll transact. So now we've transacted that onto that connection in Datomic. And then this little at basically means, so this function returns a future, and the at is basically saying, realize the future, give me the result of what it is. So if that took 10 minutes to run, this would have blocked for 10 minutes and then read. So now we've got 3 attributes in the database. We'll define some data. So here we see a bit of functional programming. So I'm defining 4 users. They've each got an ID, or an ID which is created with a temporary ID. The way that Datomic transactions work is you define temporary IDs for the things going in for the first time, And during transaction, it'll turn those temporary IDs into the real IDs in storage. Temporary IDs are negative numbers, real IDs are positive, and the result of the transaction will give you a mapping of temporary to permanent ID. So I'm just basically creating 4 users with a new temporary ID for each of them, and 4 names. And then I'm creating a vector of all of them, and then I'm adding another map to that vector with its own ID, and to link those users to the group, I'm just mapping to fetch the DB ID out of each of the users. So we can actually look at what that looks like. So we can see here that that's what's come up. So we can see that we have the same IDs in those 4 IDs or those 4 IDs, and this as a whole constitutes a transaction. So we're creating 5 entities, one of them links to the other 4. Okay, so we'll transact that. So just looking at this very quickly, we can see this is the result of the transaction. So this is the database value that you can query against as it was before that transaction succeeded. Same thing for after that transaction succeeded. All of the datums that actually happened in that transaction, and then finally that mapping of IDs. Very, very nice if you need to figure out what happened. Let's go back there. Okay. So now, this is where we get this database as a value thing. So now I'm going to get a reference to the current database. So you see I have a reference to a database. So in Datomic, databases themselves are immutable. So when you have a database value, you're pointing to a specific point in time in that database into that storage. So just to demonstrate that, I'm reading directly off the index here, the AVET index. So this is a sorted set of datums, organized first by the attribute, then the value, then the entity, then the transaction. So this will give me the 4 users, or the 4 user name datums that we have. And then we'll get them out, wherever you are. And then finally, we'll query against a different index to get the 4 datums that link the user entities to the group entity. So that's the group ID. And you can see the group ID is the same, and those are the 4 different user entities. And you can see that they all happen in the same transaction. So DHH can't make it today, guys, sorry. So first I'm just going to define a helper function. Okay, so now I'm going to query against the index to get the ID for the group. Oh, there we go, and I'm going to get DHH's ID, create a transaction, and you can see on the second line there that we're now retracting a fact from the Datomic storage. We're saying that this is no longer true. It used to be true, but now it's not. So we're removing DHH from the group. So we'll call that, get a new database value. So DB2 is pointing to a different point in time in the storage. DB1 is still pointing to the previous point in time. And now we can see that we still have all 4 users, but only 3 user associations to the group. So if we look back at the previous database, we can see that we still have all 4 users. So that is how in Datomic we can step back in time. And that is incredibly useful. So this is basically it. This is the payoff about Datomic. It's immutable. So querying against Datomic using this datums API is very nice if you need to just find a single value or a small handful of values, but it can be quite tedious. Datomic provides what is called the entity API. So given an ID, we can wrap that ID in a lazily loading entity map. So just an aside, keywords are also functions. So here we can get Aslam's name out of the entity. Let's get the reference to the group entity, and we can read the name out of the group, and we can also just get a reference to the raw user entities that are linked to into the group. So that's useless to us because it's just IDs, we can't actually read that. So just using plain old Clojure, because at this point we are really just using Clojure data structures, there's no ORM or anything involved, we can pull out the names. So just to break that down, users out of the group, map username over it, and then sort. Another really cool thing is that those relationships, those DB type ref relationships, are implicitly bidirectional. So I can, given a user, I can go back and find the user's groups. So I'm going to get Aslam's groups, find the first one, and then read off the name. And then we can see that that's how it is. And then finally, when you actually need to do really serious queries, this is the SQL analog for Datomic, you can use what's called Datalog. And some people might have heard of Prolog, which is probably older than I am. And essentially what we're doing is we're creating a series of constraints to solve over the datums in the database. So here I'm saying, find me user IDs and usernames in this database and this group name where the group IDs, group name, so now we're matching against datums, and every time you see a question mark, that's basically a variable that Datomic has to solve. So we'll find the IDs that match the name, and then using the IDs, we'll match on user IDs, and then we'll find user IDs and names. So against the second database, we have 3 people. Against the first, we have 4. Yeah? And what should drive the whole constraint solving thing home is if I do this. So I haven't actually changed anything about the constraints in the query. All I've said is, instead of using this to find it, use this to find the other side. So it's like a bidirectional thing. And that's Datalog. And the thing about using datums is that it's lazy. So you can actually walk over an entire database's index for however many gigs it is, and it'll just do the right thing in memory. Whereas Datalog is set-based. It has to pull all of the datums into memory first and then do its constraint solving. So you use Datalog when you're sure that you can fit the problem you need to solve into memory. Okay, and that's the code demo. So the talk is over. You can breathe a sigh of relief. Cognition is in Cape Town. We are hiring. If this looks like fun to you and you're tired of writing Ruby classes or JavaScript classes, then you want to do something different, then you can come and help us out. Experience with other stacks are okay, obviously. Everybody who works at Cognition learned to write Clojure on the job, myself included. And yeah, so if you're interested or if you know somebody who's interested, let me know. And finally, we have a Cape Town Clojure user group. Next meeting is not tonight, but tonight in a week, and that's at CodeBridge in Claremont. There are some notes, links to talks, to books, to websites, both for Clojure and Datomic at that link. Yeah, and that's it. Thanks. If you have questions, find me after.
No come electro por la vida.